Hey guys, welcome to lecture number 12. So today we will start something, we will continue basically with something new. I would like to talk about series this time, series of real numbers. Unfortunately, I was debating whether I should cover also a series of functions and series and power series basically, but I decided maybe not because I will need some differentiability and stuff like that as well. So probably I'll cover those topics when we talk about differentiable functions. All right, so let's get started. Well, today you will see that the series of real numbers, well, some of you have seen it, have seen this stuff in previous years. Come on. All right. All right, everybody here can see the screen, right? Okay, that's good. All right, so like I said, today we'll talk about series of real numbers. All right, now we would like to see what is a series, what are these things like series of real numbers? But before I go and talk about that, let me tell you something about the notation that we're going to use for this. So usually we denote them by the sum from n equals 1 to infinity this time of an, or sometimes we just write it like this from n greater or equal than 1 of an, or sometimes, but this is not the usual notation, we can write them like this. But anyway, usually you'll see the first two, not the third one. And now let me just recall quickly the definition. You will see that the series will also involve the convergence of a sequence, but not the sequence an, but the sequence of the partial sums. So we say that the series, and I believe you learned this in calculus 2, I think. This is where you dealt with series. We say that the series, the sum from n equals 1 to infinity of an, is convergent if the sequence of partial sums, in fact, let me write like this. If the sequence of partial sums, and this will be denoted by Sn, which will be nothing other than just x1 plus x2 plus xn, is convergent. That's what you need to know. So the sequence of the partial sums is convergent, right? So basically, in other words, studying the convergence of Sn is the same as studying the convergence of the partial sum of the series. Sorry, right? So that's the definition. Otherwise, the series is divergent, right? If the partial sum sequence diverges, then the series is divergent. Ouch. Is divergent. Okay. All right. Now, and before well, and of course, I would like to mention one thing. Let me point out this remark. Because in when the sequence, if the sequence Sn is divergent, right, the sequence of partial sums is divergent, then we can, it will converge to, it's convergent, I want to say, it will converge to some number, right? Well, the limit of Sn will be nothing else than just the sum of the series. So if the limit, let's say, as n approaches infinity of Sn is this number S, let's say, right? Then we can write the sum of this series from n equals 1 to infinity of An equals S. We can write it in this way. So keep that in mind. So the sum, the limit of the sequence of the partial sums is the sum of the series, right? Okay. Now another remark that I wanted to point out, and this is a very important one. Maybe I shouldn't put it as a remark, but let me put it as a proposition. If the series of An converges, then this sequence An, so the sequence An inside that series, then An will converge to 0. Keep that in mind. Always this will happen. And the converse is not true. And I will explain immediately why. In other words, if I have, this is important to know, that the converse is not true. In other words, if I have a sequence An that converges to 0, this does not imply that the series converges. Keep that in mind. Please do not make this mistake, because I've seen many people make this mistake. But I'm sure this is not the case for you. Okay. And the counterexample, it's quite clear. So the counterexample, so let me put the counterexample is the following. Take An to be 1 over n. And this guy clearly converges to 0 as n approaches infinity. But we will see, will see that the series, the sum of 1 over n, which we will call this the harmonic series, this guy diverges. Okay. So keep this in mind. This is very important. In fact, let me bold this. So the converse is not true. So keep that in mind, right? Okay. Of course, as you can imagine, and I don't want to write it because I don't want to lose any more time. When you have two convergent series, right? Let's say the sum of Xn, the sum of Yn, then their sum is convergent, and the sum of the series is the series of the sum, and the same goes with the product, and the same goes with you have if you multiply this by a constant. So as you can imagine, so everything is super nice when we deal with the convergent series. But now there is one thing that I would like to mention, and this is important, as you have seen in the case of sequences, there is this, there's the so-called Cauchy convergence criteria, and the same thing happens here. So Cauchy criterion for convergence. And there are plenty of others, but let me mention this one. Right. And it says the following. The series, the sum from n equals greater or equal than 1 of, let's say, okay, an is convergent if and only if, right, for all, I'm going to write it like this, for all epsilon greater than 0, right, there exists a rank n epsilon, right, in n star. When I write n star, I mean n going from 1, n greater or equal than 1, right, such that for all n greater or equal than that rank, n epsilon, and for all p greater or equal than 1, we have that the absolute value, okay, I'm going to write it like this, and I will explain immediately what do I mean by that. Xn plus 1 plus xn plus 2 plus all the way to xn plus p. This in absolute value is strictly less than epsilon. What do I mean by that? In other words, this says the following. If I have a oh my God, I put x here instead of, okay, let me write it here with x. All right, so in other words, this tells us the following fact. So if I'm dealing with a convergence series, then I just look at the first n terms as n is very large, and I don't care about what happens to the next one. So the ones after xn, so xn plus 1, xn plus 2, xn plus p, I neglect them. I don't care about them. They're when I add them up, they're epsilon. So basically, they're nothing. They're small enough. All right. So this is the Cauchy criterion for convergence, and there are plenty of others, and I would like you to remember those. I would like to mention, maybe I'll mention a couple of them, but the others, I would like you to remember them from calculus too. I think you'll learn a bunch of them. And now what I would like to say is two important series, so examples. So two important series. And I will deal with one of them. Then the first one is the geometric series, right? Which basically says that if I have a number x, which is an absolute value is less than 1, then the series, this guy here, the sum from n equals 0, I'll start from 0, x to the power n, this will be 1 over 1 minus x. So this is the geometric series. And 2, the harmonic series, the generalized harmonic series, let me put it like this. Which says that this series, and we'll start from 1, of 1 over n to the power p, right? And this has two options. So this is converges if, and let's just say p is, so p is a positive. So, okay, let me write it here. Okay, p is positive. Then this series converges if p is greater than 1 and diverges if p is less or equal than 1. Right, in the case of p, when p equals 1, we have the harmonic series. So the harmonic series And maybe I'll just show you it in this example. 1 over n diverges. Right? And the way we see this, there are plenty of ways to see it. Well, if you look at the partial sum, right, of the harmonic series, nothing else than the harmonic sequence. And you know that the harmonic sequence is the divergence. So there you go. But there is another way of proving this, and I'll just say the Cauchy condensation criteria. For some reason, this is criterion. This is not done in the calculus 2 in the calculus textbooks. I don't understand why, frankly, because it's a very useful criterion. Basically, it says the following, and I'm going to write it in this way. The series, these two series, two to the n times x up times x up 2 to the n, have the same nature. What do I mean by that? Both converge or both diverge. Let's just write it this way. Both either converge or diverge. So that's what you need to know, both of them. So there is no way you can say that one of them will converge and the other one will diverge. No, that's not going to happen. So this is like, wow, it's pretty amazing. So let me show you a quick application. And the quick application I have in mind is the harmonic series. So the harmonic series. Which is the sum from n greater or equal to 1, then 1 over n. Okay, so this, and I'm going to write it like this. So by the Cauchy condensation criterion, I'm going to write it in this way. The harmonic series, 1 over n, right? And then I'm going to write it like this. So it's similar to. You will see that I'll write once I will discuss a bit about the comparison criteria, both limit and inequality comparison. You will see that I will use this notation, especially when I'm implying the limit comparison test. But anyway, so this guy will be similar to this guy. 1 over 2 to the n, right? But this guy will be nothing else than just 1. And this is divergent. And we're done. That's it. You see, one line. And the same goes for so the same goes for the generalized harmonic series. Right? So in fact, and I'll leave it to you as an exercise, because, well, you'll have there 2 to the power 1 minus p to the n. So that's a geometric progression, but that's a geometric series basically, and then you will see how how to deal with it. I'll leave it to you as an exercise. Anyway, now I want to veer towards something else. Comparison tests. So comparison criteria, let's say, for series. And what do I mean by that? The first one that I have in mind is what I call the inequality comparison test. Right? So the inequality comparison test says the following. Okay, I'm going to write directly two series, the sum of Xn and the sum of Yn, right? Series of real numbers. Okay. We have the following. Then we have the following. How should I say it? Then if, well, you can write this in plenty of ways, but I'm just going to write it in one way. If, let's just say, because I said real numbers, but I will say that if absolute value of Xn is less or equal than Yn, and no, let me write like this, such that, because such that, right, this inequality holds true for all n greater or equal than 1. Okay, now, then we have the following. If the series, the sum of Yn is convergent, then the series of Xn is convergent. If the series of Xn is divergent, then the series of Yn is divergent. Of Yn is divergent. You see? So, but the only thing you need to keep in mind here is this guy right here, this inequality. That's the important fact, because you can remember this as Yn dominates Xn. So this is how you remember. So it's less or equal. Well, Yn dominates Xn. If the series of Yn is convergent, then there is no way you can have the series of Xn divergent, because Yn will dominate Xn. So this is how you remember. But then the other way around, if the series of Xn is divergent, but Yn dominates this of course, is the series of Yn is divergent. So it's very easy to remember. All right, and that's the inequality comparison test. But you know, there are plenty of equivalent formulations of this, but basically this is what it is. And now the second one is the limit comparison test. This is very important. So the limit comparison test. And then I'll provide an example. In fact, I'll take again the harmonic series and I'll show you how this works. So the limit comparison test says the following. How should I say it? This time, so if the sequence of Xn is positive, and in fact, let me write it in this way. If Xn and Yn are sequences such that such that, let's say, Xn is positive, right, for all n. Let me write it this way. So Xn is positive for all n. And there exists this guy, the lim as n approaches infinity of Xn over Yn is L, which is positive, right? This is the very important condition. Then we can say that then the series of Xn and Yn are either both convergent or divergent, or both divergent. So they have the same nature. That's what you have to keep in mind. Okay, so this is the limit comparison test. As you can see, it's a little bit different than the inequality comparison test, right? If you look at it. All right, and now let me show you a quick example. And the quick example is, again, the harmonic series. Man, I hope I don't, okay, that's the harmonic series. So, which is this guy here. You see, let me show you, so let me denote this guy. So let an to be 1 over n. All right, what do you know about this? Remember that we proved this inequality. Remember that, and yes, we proved it, or at least I told you last week. Remember that 1 over n is greater or equal than ln of n plus 1 minus ln of n. For all n greater or equal than 1, right? So this implies that, well, let me take this guy to be Bn. And now I'm looking at the series of Bn. So the series, the sum of Bn, which is this guy. And what can you tell me about this series? Can you tell me something about it? What can you say? We have, you see the difference of any two consecutive terms, ln of n plus 1 minus ln of n. What can you tell me about it?
You say that it's less than or equal to 1 over n, the harmonic series?
If you look at the partial sums, let's say, of this, aren't there like telescoping sums?
Oh, so that's where the first, everything but the first and last term will cancel out.
Exactly, exactly. You have, so the partial sums, the partial sums of this is, what is it? Is ln of n plus 1 minus ln of n. ln of 1, sorry. Which is ln of n plus 1, which diverges. Goes to infinity as n approaches infinity. So this guy diverges. Right? And there you go. So n is greater or equal than bn, the series of bn diverges, then the series of n diverges, right? So by the inequality comparison test, the harmonic series diverges. You see, you have another way of proving this. So you have Cauchy condensation test, then you have the inequality comparison test. What about again, let's apply the limit comparison test. So let's say, moreover, we can apply the limit comparison test. What are we going to do here? So, well, we know that. So we use the fact. Okay, I'm going to use the limit of functions, but I'm sure you know this. We use that the lim as u approaches 0 of ln of u 1 plus u over u is 1, right? Or equivalently, we can write this as ln of 1 plus u is similar to u as u approaches 0. So, right, remember this? This is from Calculus 1, I believe. And once we have this, so then we can say that 1 over n is similar to ln of 1 plus 1 over n as n approaches infinity. But this guy is the same as ln of n plus 1 minus ln of n, and the same story goes, right? The series, so the series of 1 over n is the same. We can write this as the series of ln of 1 plus 1 over n, which is the ln of n plus 1 minus ln of n. But this guy, as we have previously seen, this guy diverges. So by the limit comparison test, this diverges as well, right? Is it clear?
Yeah.
Yep.
All right, that's good. So you see, there are plenty of ways to play with this. I don't know. There are some other things that I would like to do, but there's many ways, many things to do. But maybe no, I'll stop anyway with the theory, because I would like to dwell more on examples as well. You know, there are some other criteria, but you can remember, you can revise them. I will suggest you go and look at the Calculus 2 textbooks. There are plenty of them. But anyway, let's see some problems. And the first problem that I have in mind, so problem 1, is the following. All right, let me go with the Putnam. There's a nice problem. It was a Putnam, I think A1 1994, which says the following. Suppose that a sequence A1, A2, A3, and so on, right? Suppose we have this sequence satisfies this inequality. Well, 0 is less than n, so the sequence contains only positive terms, and is less or equal than a sub 2n plus a sub 2n plus 1, right? For all n greater or equal than 1. Prove that the series the sum from an diverges. Wow. Okay, I want you to look at it, think about it for a couple of minutes. So if you see it as a Putnam A1, you should think that this should be easy, right?
could we try to prove that a sub 2n plus a sub 2n plus 1 diverges, and since that's greater or equal to the sum of a sub n?
No, it's the other way around.
Oh, okay. So you prove that a sub n diverges.
Then the series of a sub 2n plus a sub 2n plus 1 diverges.
Gotcha.
But this doesn't help you for the problem.
No.
It's actually easier than you think. Think of what if the series, well, you see, that's one thing. When you look at this, not just this type of problem, usually when you have a problem and you feel like you don't have enough conditions, right, to prove something, maybe you can come up with an extra condition, just like that. So what would that be? Maybe if you want to see what happens if the contrary is true, right? If the series of and convergence, maybe we'll get a contradiction. Maybe that's easier to prove, right? So let's see. And maybe we should exploit that condition there as well. So suppose by contradiction, that that the series converges, right? So suppose that the series of these converges. Okay. Then what do we have? So keep in mind that we're going to do the following trick. And the way we're going to do them is in the following way, because I'm going to exploit this inequality here. See this one here. I want to exploit it. And also we'll take into account the fact that an is positive. So then we have, I'm going to write it in the following way. Then the sum of this series, so I would like you to pay attention here, an will be how should I say it? So I'm going to leave the first term and then I'm going to group the others. So this would be A1 plus the sum from n greater or equal than 2, let's say, of an, right? But this will be greater or equal, pay attention, because now I'm going to use the fact that wait. So A1, then A2 plus A3 will be greater than A1. Okay, let me write it in this way so that you can see it. A1 plus A2 plus A3 plus what else we have? So A2 plus A3 will be greater than A1. Then I'll have for n equals 2, I'll have A4, A5, right? And so on. And if you look at this guy, this would be so we can write it in the following way. So this guy is, so let me think a bit. So is it A1 plus the sum of these series? Here I'll have, let's say, AN, A sub 2n, sorry, plus A sub 2n plus 1. I can write it in this way, right? And now this guy, now, right, is it clear? Okay, let me write it here. So this guy is nothing else than A1 plus the sum of A sub 2n plus A sub 2n plus 1. So I'll group them in this way, right? I'm just going to leave the first term, and then I'm going to take two, A2, A3, A4, A5, and so on. And I'm going to group them like in pairs like this. But this guy here, we know that is greater or equal than A sub n, right? So this will be greater or equal than A1 plus A sub n, which will be strictly greater than A sub n, the sum of this series. Well, look, what did we obtain? That the sum of an is strictly greater than the sum of an. False, right? Where did the contradiction come from? From the assumption that A is the sum of A and converges, right? So the sum of an diverges. That was it. That's the end of the problem. It was very easy, wasn't it?
Yeah, once you figure out you have to do proof by contradiction, I think the rest.
Yeah, that's it. So you see, sometimes you just need some idea, and that's the problem, right? So you see, that was a Putnam A1 1994. So you just needed an idea and to exploit the fact that, and of course we have to know that the terms are positive, otherwise, right? That's a common sense condition. All right, so that was the first problem. Let's see another problem, problem 2. And this time, there was this Putnam B1 in 2016. Again, well, I won't say super easy, but you'll see that. So the problem says the following: let x0, x1, x2, and so on be the sequence such that x0 is 1, sorry, and for n greater or equal than 0, we have the following recursion. I think we've dealt with some recursion. So xn plus 1 is ln of, so is the natural log of e to the xn minus xn. Right? Show that the infinite series, so I'm just going to state it the way it was in the contest. Show that the infinite series x0 plus x1 plus x2 plus so on converges and find its sum. Okay, I want you to think of the problem for a couple of minutes and then we'll discuss it. And I will tell you the real danger of this problem. What is the real danger of this problem? Because you see, in fact, I would like you to think of it and then we'll discuss. So how would you approach? Let me tell you what is the real danger of this problem. So the real danger of this problem is the following, is that you see, when you have this recursion, you don't discuss the convergence of the series without discussing in the first place the convergence of the sequence Xn. That's very important. So first, this is very important because this is how you lose points. I remember one time I was at Pitt when we were discussing the problems after the Putnam, and then one of my students, and he was the very best in our team, he said like, I assumed that the sequence is convergent. And I was like, man, that was basically the whole problem. Right? You cannot just assume that. You have to prove it. So unfortunately, he got 2 points instead of 10. He thought that that was too easy. Anyway, so make sure you don't do this mistake when you have something like this, because you need to make sure what happens to Xn, and you will see why. So first, we discuss the convergence of Xn. This is very important. All right, before I even talk about any series. So you see, it's a recursion there, and the first term, x0 is 1. All right. Well, I believe that, so first, let's prove by induction that Xn contains only positive terms for all n greater or equal than 0. And in fact, this is not trivial, because we would like to see why this happens, right? So for n equals 0, we have x0 equals 1, which is positive. And now suppose that Xn is positive for all n. And we want to show that Xn plus 1 is also positive. All right, let's see how. Well, by the elementary inequality, e to the u is greater or equal than u plus 1 for all u greater than 0. And I will leave this to you. In fact, I would like to prove this. I will address this later. It follows that Xn plus 1, which is ln of e to the Xn minus Xn, and we know that the function, the natural log function, is increasing. This will be greater or equal to ln of Xn plus 1 minus Xn, which is ln of 1, which is 0. So Xn plus 1 is greater than 0, is 0, right? So Xn plus 1 is greater than 0 for all n. So by the induction, induction principle, Xn is greater than 0 for all n. Okay, so we have this, right? You see, we use this inequality here. Well, you can prove it using differentiability, but we can do it without it. This, so let's address this. So fact, for u greater than 0, e to the u is greater or equal than u plus 1. All right, and let me give you a quick proof of this. Okay, I'm going to do it in a tricky way. So we have that 1 plus u over n to the power n by the Bernoulli inequality, and I think I've discussed this in the very first lecture, is greater or equal than 1 plus u, right? But as n approaches infinity, u plus u over n to the power n will approach e of u. So there you go. And that's it, right? And you have two quantities. The first quantity is greater or equal than the second one. You take the limit as n approaches infinity. So the limit, the inequality for the limits is preserved. So there you go, right? I hope it's clear. All right, so it's kind of a big deal for us to, just look at the sequence to prove that Xn is positive. But now, what else can we do here? Well, we can do something else as well. What about the monotonicity? So the recursion, can we rewrite the recursion in an equivalent form? So let me write it again. Xn plus 1 is ln of e to the xn minus xn. Can be rewritten as what? Can you tell me? How can we rewrite that?
E to the power of xn plus 1?
So e to the power xn plus 1 equals what?
E to the power of xn minus xn?
Minus xn, right? So we can write it in this way. Right? And now, so xn, if you want, is e to the xn minus e to the xn plus 1. Okay, for n greater than 0. So let's keep this in mind. All right. So I know that xn is positive, right? Since xn is positive, it follows that what? That e to the xn is greater than e to the power xn plus 1. But since the exponential function is increasing, it follows that what? That xn is greater than xn plus 1 for all n greater or equal to 0. So the sequence is what? Decreasing. We know that since it is decreasing, it follows that, so x0 will be the upper bound, right? And since since xn is bounded, so it's between 0 and 1, by the monotone convergence theorem, it follows that xn is convergent. Wow, okay, finally. But it's convergent to what? Now the question is, what is the limit of xn? So question is, what is the limit of xn as n approaches infinity? So let's look at the recursion again. So by passing to the limit in the recursion, we can, by passing to the limit, we have done this, to the limit in the recursion, we get, let's see, what do we get? So we get x L, let's say L is e to the L minus e to the L, which is 0, right? And that's it. So the limit is 0. So this so the limit as n approaches infinity of xn is 0. You see, there's a lot of things to write here. You see, that's the big portion of the problem. And now let's go back to our problem. You see, I'm not interested in the limit of the sequence, but more I'm interested in the sum of the series. Right? Look at what I'm asked to, and also not just that, I want to find the sum of this. All right, so let's do it. So the sum of this series is nothing else than this studying the partial sum sequence. So the partial sum sequence let's say Sn and greater or equal than 0, well, given by Sn is x0 plus x1 plus x2 plus all the way to xn, right? Is what? Definitely it's increasing, right? And what can we say about it? So who is this guy? Is, okay, I'm going to write it in this way, is the sum from k equals 0 to n of xk. But again, we're going to appeal to our recursion. Is the sum from k equals 0 to n of xk. Keep in mind that xk, if you go back, was nothing else than just e to the xk minus e to the xk plus 1, right? Look at the relation. You see the box, so this would be equal to e to the x k minus e to the x k plus 1 is, and now this will be a telescopic sum, right? Okay, I'm going to write it like this. So e to the x0 minus e to the x1 plus e to the x1 minus e to the x2 plus e, let me write the last before the last one. So e to the x n minus 1 minus e to the xn plus, and the last one is e to the xn minus e to the xn plus 1. As you can see, all of them just go away. Look at this guy. This with something from here. This goes with this one. This will something from here. And the last two terms that stand up are these two guys, right? But we know that x0 is 1, so this would be nothing else. So this is 1 minus e to the power xn plus 1. And now the sum of the series will be nothing else than just so let me write like this. Finally, the sum of this series of an is nothing else than just the limit of the partial sums by the definition, which will be the limit as n approaches infinity of 1 minus e to the power xn plus 1. But we know that the limit, you see now the limit is 0, and we have to prove this. So it will be well, wait, did I make any mistake here? Because it gives me, let me see. So it's 1 minus, okay, so this would be, so the limit of that, so it's 1 minus 1, which will be 0. That's strange though. Let me see if maybe I made some mistakes. I think, wait, well, of course, I'm stupid. If you guys, this is not the one here, it's e to the power 1, which, oh my God. E to the power 1 minus this, which is e minus 1. That's it. Does it make sense? Because I remember the result was the e minus 1. I was like, and here it's the mistake again. E to the power 1. I forgot to put the e there, and that's it. That's the end of the problem. As you can see, it was a bit involved. You see, you have to write all these details and all this stuff. So yeah, but it was well, but it was a B1. Probably back in the 90s, this shouldn't have this. I don't think this could have been a B1. Probably a B3. So as you can see, the difficulty is it's higher now. Anyway, now let me do another problem. So problem 3. Which is it's a similar with this one. Anyway, so the problem says the following: let n greater or equal than 1 be a sequence such that the first term a1 is a real number, and a sub n plus 1 is sine of a sub n for all n greater or equal than 1, right? Show that the series the sum from n greater or equal than 1 and an of n diverges, and while the series of n cubed converges. Okay, I want you to look at the problem. You see, that's a funny thing. If I have this kind of recursion, then the sum of an diverges, well, the sum of an cubed converges. So that should tell you something. Maybe, I don't know, think about it. So based on what we said in the previous problem, what would you do first before you even go and talk about the convergence or divergence of those two series? What is the first thing? Say that again. Exactly. We look at the sequence and we study the convergence, right? So first, we study the convergence of N. That's the first thing that we do. You see we have a recursion there, so maybe we can do that. All right, let's see. In fact, I'm going to leave it to you, and I'll leave this as an exercise. One can prove that, because I don't want to lose more time with this, that N converges to 0. And this was an exercise for you. Again, you use the monotone convergence theory, you study the monotonicity, you know that sine of x is less or equal than x. So sine of An is less or equal for all x, for all real x, so that's why you don't need positive. So sine of x will be, sine of An is less or equal than An, so it's decreasing, right? Then you can show that it's clearly bounded because sine of An is between -1 and 1, so An plus 1 is between -1 and 1. So therefore it's convergent. So you pass the limit in the recursion, you have L equals sine of L. 1 is equal, 1 L is 0, so that's it. Anyway, it's pretty straightforward. And now we would like to see something else, maybe because you see, if you look at these two guys here, if you look at these two series, this guy here and this guy here, you see, when I raise to the power 1, here, let me put here 1, it's divergent. When N is raised to the power 3, it's convergent. So maybe N will behave like some kind of a harmonic sequence, right? Like 1 over N to some power, and we have to determine that power. And the way we do this is maybe we should look at this sequence. Maybe N is the square root of N or times a constant. So the idea, the trick here, so the idea is to look at okay, I'm going to just say it the way it is, the asymptotic behavior, whatever that means, I'll explain immediately, behavior of N. And in fact, I just need the first asymptote. In other words, I would like to see how An behaves. So we look at the sequence. Let's just say this guy, 1 over N An squared. And I'll explain immediately what do I mean by that. And in fact, at the limit of this sequence, to be more exact. So we have that the lim as n approaches infinity of 1 over N An squared. This would be, and I'll write it in the following way, the lim as n approaches infinity of 1 over An squared over N. Right? And now, since An converges to 0, 1 over An squared will diverge to infinity. So I have infinity over infinity. And now I can apply the Cezar-Stolz. And this will be the lim as n approaches infinity of 1 over An plus 1 squared minus 1 over An squared, everything over N plus 1 minus N. And this would be equal to the limit as n approaches infinity of 1 over An plus 1 squared minus 1 over An squared. But now if we replace this in the recursion, this would be nothing else than the lim as n approaches infinity of 1 over sine squared of An minus 1 over An squared. And now I'll leave this to you as an exercise. So to show that this is 1/3, this is because, let me write it here, the lim as u approaches 0 of 1 over sine squared of u minus 1 over u squared. So this guy here is 1/3. So try to use L'Hopital rule. Right? So this is 1/3. So this means that, well, since this means that n squared will converge to 3 as n approaches infinity, or you can say that the square root of a of n times an will converge to square root of 3, right, as n approaches infinity. So in other words, this is how we get the asymptotic behavior. So we apply the Cezar rule. So in other words, this guy an will behave like what? Like square root of 3 over square root of n as n approaches infinity. So this is how it's going to behave like. And now it's quite clear what happens. So the series the sum of an will behave similarly as this guy here. Anyway, I don't care about the constant, just take it out. Look at this guy, 1n to the power 1/2. What can you tell me about this series? Is the harmonic series, the generalized harmonic series with exponent 1/2, which is less than 1. So this guy will diverge. So this diverges, right? So therefore, by the limit comparison test, this series will also diverges. Also, for the cube one, as you can see, the situation will be a little bit different. So this would be, again, I don't care about the constant. Let me, anyway, it's a constant cubed here. Okay, let me write it. One over square root of n cubed, and this would be whatever 3√3 times this series 1 over n to the power 3/2. Now, what can you tell me about this series? This guy will converge because it is the generalized harmonic series, but with the exponent greater than 1, and that's the problem. See, it was tricky. All right, I still have, okay, I'm gonna go over time, sorry about that, but I want to talk about one more problem. It's one of my favorite Putnam problems, in fact. So that's well, there are some details that I'll leave them to you. So problem 4. So this was a Putnam B4 in 1988, right? Okay, and the problem says the following. Let an greater or equal than 1 be a sequence of positive reals such that the series the sum of an converges. Show that the series this guy an to the power n times n plus 1 converges also. It's a very nice and tricky problem, I would say. So let me just dive directly into it. Let me explain it. You see, it depends on n everything there. So you cannot just say like n is less than n over n plus 1 less than 1, then because everything depends on n. It's not just a fixed constant. So we need to do something about it. And the main idea is to use the inequality comparison test. So we have, in fact, I will look at this guy here, this term here, an to the power n over n plus 1. And I'm going to write it in the following. So we write an to the power n over n plus 1 as an times an times an, right? N times. And what I'm going to do is the following. I'm going to do the following trick. So we have that the n plus 1 root of an times an times n times. This can be written as an times an. And now I'm going to break one of the an's into 2 square root of n. Right? And here I'll have how many times? N minus 1 times. Okay, so I have it this. And now this guy, I'm going to write here, is less or equal by the AMGM inequality. Is less than n minus 1 an, right? Plus 2 square root of an, everything over n plus 1. And now, and this guy, let me just say that this guy is an to the power n over n plus 1. And now we look at the series of these two guys. So now we look at this series. We look at the series, the sum of n minus 1 an plus 2 square root of n over n plus 1. This guy will be nothing else than just, I'm going to break this into two series, n plus 1 plus these two series here, 2 square root of an over n plus 1. All right, and what I need to do right now is to study the convergence of these two series. So the first series, n minus 1 times an over n plus 1. Anyway, it doesn't really matter. Will behave asymptotically as this series of an, because the limit as n approaches infinity of n minus 1 over n plus 1 is 1, and this converges. So this guy here is convergent. Let me look at it. This guy is convergent. Now let's look for the second one. The second one is not as trivial to see. So, but the second one will converge as well. Converges as well. Because we will apply the inequality comparison test, and we'll have that plus 1 over n plus 1 squared is greater or equal again by the AMGM. Man, but this time for two numbers. Times 2 square root of an or 1 over n plus 1 squared, which is nothing else than our series. 2 square root of n over n plus 1. But now, the series this series, the sum of n plus 1 over n plus 1 squared is nothing else than just the sum of these, sum of n plus the sum of 1 over n plus 1 squared. But both of these guys, is convergent, we know from the hypothesis, it's given in the problem, and this is just a harmonic series with exponent 2. Again, this is convergent. And by the inequality comparison test, it follows that this guy is convergent as well. So by the inequality comparison test.
So I have a quick comment for the convergence
Yes.
of the harmonic series. Since p is greater than 1, it converges, right?
Yes, correct. Test, it follows that this guy converges, right? All right, so finally, we can say that this guy is convergent as well. This guy here. So we have finally, by the inequality comparison test, it follows that the series of this is convergent. So let's write it again. Finally, by the inequality comparison test.
So basically, you have to use the GM-AM inequality to set up the comparison test, right?
Yes. Say that again?
You have to use the AM-GM inequality to set up the inequality for the comparison test.
Yes, exactly. When you compare those two sequences. So you have a sequence Xn is less or equal than another sequence Yn, but you get that inequality by using this tricky AM-GM twice, you see? In fact, there are two problems in this. Anyway, so it follows that this guy is convergent. And that's it. Well, it was pretty involved, right? All right, I'll stop here for today. Well, I'll send you a worksheet with problems to work on, and we'll meet on Thursday for the recitation, and then we'll discuss the problems. All right, guys, you have a good rest of the day. Take care. Bye-bye.
Bye, Cezar.